Over the last 3 episodes, we met the SFC, the muscle that spins the shaft. We met the SEE, the brain that feeds the field. And we saw how each one works individually. But a real startup isn't 2 separate stories. It's one tightly choreographed sequence with dozens of interlocks, signals, and permissives firing in exact order. Today, we walk through the entire thing, second by second. Before a single command is issued, the control system checks a long list of permissives. Is turbine enclosure ventilation running? Are all protection relays healthy, with no active trips? Is the SFC breaker closed and ready? Is the generator breaker confirmed open? Is cooling water flowing? Is lube oil at pressure? Only when every permissive shows true does the DCS allow the start command to be issued. Miss one interlock, and the sequence simply will not begin. Start command issued. First response. The SEE's field breaker closes, and the AVR begins ramping up field current in field flashing mode. Within seconds, the rotor becomes a real electromagnet. The DCS confirms, field established. One status bit, but it's the trigger for everything that follows. Without this confirmation, the SFC is not permitted to begin. The sequence is strictly interlocked, one system waiting on the other. Now the SFC breaker closes, and the inverter begins producing output at near zero frequency. The speed feedback signal from a shaft-mounted pulse pickup starts climbing from 0. The control system ramps frequency on a defined acceleration curve, often a fixed rate, like 1 Hz per second, sometimes holding at specific speeds to check vibration or bearing temperature. Every second, the DCS logs frequency, current, and speed together, a live trend any commissioning engineer recognizes instantly. At the firing speed set point, typically 15 to 20% of rated speed, the sequencer issues the fuel valve open command. Igniter spark. Flame detectors, usually ultraviolet sensors, must confirm stable flame within a set time window, or the sequence trips on failure to light. Once flame is confirmed, the turbine's own combustion begins contributing torque. The SFC doesn't stop yet. It keeps assisting through the critical acceleration zone, where the machine must cross mechanical resonance points quickly, not linger on them. As the turbine approaches self-sustaining speed, torque contribution flips. The turbine is now doing the work, and the SFC's current draw falls towards 0. At a defined speed set point, the control system trips the SFC breaker. The inverter shuts down. Its job, for this start, is complete. The shaft keeps accelerating on combustion power alone, climbing the last stretch toward full synchronous speed, 3,000 or 3,600 RPM, depending on grid frequency. Near rated speed, the AVR shifts from manual field control into full automatic voltage regulation, matching generator voltage to the grid. A synchronizing check relay compares voltage, frequency, and phase angle between the generator and the grid, and only when all 3 align within tolerance does it issue a permissive to close the generator breaker. The unit is now on the grid. The SEE settles into continuous duty, regulating voltage and reactive power for as long as the unit runs. That's the complete sequence: permissives, field flash, frequency ramp, ignition, disconnect, and synchronization. The same choreography plays out at every start, on every unit, at every plant. Correct, error, and ROF are included. Next episode, failure modes. What happens when a step in this sequence doesn't go as planned? Subscribe, and I'll see you there.